All right, thanks everybody. I'm Ben Fuller, this is SoK, so it's going to be necessarily incomplete. I think I have 14 out of 186 citations in the talk, so that's a rough approximation of how much content I have. This is joint work with Mayank, Arkady, Emily, Ariel, Vijay, Rich, Darby, and Rob, and I think that's the whole list. So we're going to be talking about the trade-off between data utility and data privacy, in particular large data storage. So we've covered this many times in the symposium so far, but data has tremendous value to organizations. It's lifeblood of a lot of companies. In fact, there's even websites you can go to where you can find out how much your data is worth, and I'm sure they steal it as soon as you tell them how much it's worth, but you can kind of figure out how much value you have based on your privacy. So organizations rightfully take a lot of pride in being caretakers of this data, and it has tremendous value to them. But anytime you have value, it also creates risk. So we don't need to list the large number of privacy breaches, but I'm going to do it anyways. These vary across sectors, from defense industry to consumer to government to academia to whatever you want, to cheating on spouses. And this led last year to Bruce Schneier saying that data is a toxic asset. So the question we want to ask is it possible to balance this tremendously huge value that exists in having data stored and processed and searched on, along with the risk that comes from having this data? Okay. So I identify as a cryptographer, as do some people in the room. The natural thing I would say is if there's risk to data compromise, we should be encrypting data. And it's not quite clear what that means. If I have a large data set I want to search over, generally we have this setup where we have a bunch of clients connecting to a bunch of different database servers with data provided by some owner, and this is all processed on some back-end storage. So I'm going to consider a slightly simplified model today where we only have a single client and a single database server. If you're interested in the more complex setting, come talk to me. Not everything translates over to this more complex setting. So when I say let's encrypt data, well, who am I trying to protect from? What threat do we care about? Well, one thing we could talk about is just an adversary sitting on the network somewhere. And here it's clear what we do, right? We use standard protection mechanisms such as TLS to protect these channels. Okay. Now, you could also consider, well, maybe what we care about is an adversary who compromises the back-end storage system. And here, again, we have pretty reasonable solutions. In fact, laws such as HIPAA require you to encrypt data at rest, and this capability exists in many modern databases. You have kind of the coarse grain, just encrypt the entire data set on storage, and then modern databases also allow you more fine-grained encryption. So you can encrypt, for example, a single attribute, a single column under a particular key. So this we have a pretty good handle on how to do too. Well, you might say, well, the thing we're worried about is actually having a malicious client. And here, the issue isn't really providing encryption, but it's providing good access control on the server. And this, I won't say we've solved this problem, but we at least know the right place to look for this. Okay. What we're mostly going to talk about in this talk is what happens when you have an adversary looking at your database server itself. And here, providing protection seems a lot more difficult. And the reason for this is that the server still needs to be able to process queries, right? If I have a 100 terabyte database, as a server, I need to be able to get you the 100 relevant records, and so I need to be able to figure out what those records are. And so there seems to be this inherent tension between the server has to learn something in order to actually give the client back the right records, but we don't want it to learn anything because then this data could be compromised. Okay? So we're going to talk about today cryptographically protected search. And this is a set of schemes that explore this trade-off. So they try and say, can we get the least risk possible out of storing this large-scale data, at the same time keep all the rich utility that we've come to know and love from databases, which there's an entire great community that drives value out of these large-scale data sets. The first straw man you can talk about is, well, we don't worry about the server at all. We encrypt data at rest, and this has high risk to it, but high utility because the server can do anything it wants. The second straw man, which I briefly mentioned, is, well, we don't have the server process at all. Every query, it gives you back the entire data set. And obviously, this has lower risk, but you're not going to scale up to any reasonable sized database. I also want to mention, I'm not going to talk about homomorphic encryption or multi-party computation. These techniques, although they solve the problem in theory, are still way too slow to use for any practical sized data sets. Okay. I've been calling this cryptographically protected search. There's some other terms in the literature, including symmetric searchable encryption and property preserving encryption. This is an umbrella term over both of those. And so the reason why we thought it was important to systemize this is, well, one, there's been a large volume of work. We have, I think I counted 50 plus papers on ePrint in this. There were multiple sessions at CCS last year. There's, I think, at least 4 papers at S&P this year. Second, we've seen, with the explosion of secure messaging, we've also seen an explosion in commercial products that are doing protected database search. And these vary from startups whose entire business model is on protected search to large companies like Google and Microsoft. In addition, you've seen large-scale government investment in this project. So IARPA, which is the intelligence version of DARPA, has been working on this problem since 2006, and our team served as the evaluation team for that project. So you've seen investment and interest from a wide variety of actors. Okay. But just interest in a space isn't enough of a reason to systematize. The other thing that's really important is I laid out this X and Y axis. And I said there's data functionality and risk of data compromise. It's not clear what either of those things means. And so what I'm going to try and walk through in the rest of the talk is how we try and pin down a little bit more, what do we actually mean when we say, oh yeah, something has very low risk and very high utility. And I'm going to start with the risk of data compromise. Okay. Cryptographers love making up definitions. So you'd think this would be kind of an easy thing. We'd come up with 3 or 4 definitions of security, and then we'd say, oh, this one's stronger than this, and this is kind of the strongest definition of security. That's not what happens at all in this space. And the reason for that is because protected search schemes, to be efficient, necessarily reveal some information about either the underlying data set, the query, or the result set. You have to do this if you want to get anything close to unprotected database performance. And this information is called leakage or information leakage. And this makes things really tricky because you can provide the strongest looking definition and then provide leakage to one party that says, oh, they learn all the secret state in the system. You can go through a perfectly valid looking security proof while providing no protection at all. Okay? And what we find is in the literature, everybody they come up with leakage functions that make their proofs work. And so you can have 2 different papers that are leaking the exact same things, but they're stated in different ways, and it's not possible for 2 people to tell. And so there's been no way to actually compare, is this system more or less secure than this other system? Okay, so one of the things we did in this work is we defined a common language for leakage, and we defined 5 types of leakage of increasing impact. So the first we call structure. And this is information that can only be hidden by padding. So if you have a query result set that returns 3 records, you have to leak that information unless you're just going to pad it. And you can pad on kind of a small scale, but there's very little hope that somebody at the server is not going to be able to distinguish between a query that returns 0 records and one that returns 1,000,000. You're not going to make every single query you process return 1,000,000 records. Okay? So this is the least harmful, but actually the example I'm going to show coming up only relies on this information. The second type we call identifiers, and this is not information about the underlying data itself, but is information that persists throughout time. So you might learn that the same data record is returned across multiple queries without learning anything about the underlying data. Okay? Third, we call predicates, which is identifiers that persist over time, as well as a bit of information. This might be some statistics about the data without revealing the actual record itself. Equality, which allows you to test if two fields are equal and essentially allows you to compute frequency statistics over the data. And lastly, ordering, which allows you to not only test equality, but come up with a fully ordered list of attributes. There's an implicit 6 type, which is just you reveal the data. Okay. Now, what we find is not only are there are these 5 different types of leakage, but we find that there are schemes that leak this information at initialization for the entire data set. And then there's schemes that only leak this information at query for the relevant records. And we find that essentially all 10 of these possibilities exist in the literature somewhere. And the reason this is important is in the last couple of years, we've seen people take these leakage functions and turn them into actual practical attacks. So I'm going to give just a toy example of what those attacks look like right now. So we have an example hospital data set. We have birth month, length of stay, gender, diagnosis, and social security number. Okay? And all we're going to assume is that the server sees which field is queried, how many records come back, and that records are identifiable. Okay? I'm not going to assume anything else about the way this system works. And so what we can do is, just based on seeing these queries where we know nothing about what was queried, we can build a histogram where the x-axis, rather than having true values, just has some masked values. Okay? And I just create this unique identifier based on these masked values. So what I can then do is, we've heard about differential privacy already today, I can use statistical priors. So I can go, for example, to the National Institutes of Health, and I can download how long people stay in hospitals. And this is on your right, on your left. This is how long people stay in hospitals. So the longest, most people stay in hospitals for 4 days. And so we can actually then recover, okay, that query that we saw was for people staying in hospitals in 4 days. Okay. Now, this is a very simple attack. We're just basically matching histograms. But you can make this attack a lot more sophisticated. In fact, people do this, and they do this, well, for one reason, they do it if their statistical prior is inaccurate, or if the number of records returned by queries is much closer than what we see in this diagram. And importantly, this attack is only going after a single field here. A lot of leakage attacks actually exploit correlation between fields. So for example, length of stay and gender are correlated. Men tend to stay in hospital for a longer time than women do. Okay. And so what we find based on this leakage language is we find 3 main approaches to protected database search. The first of these we call the legacy approach. And these are schemes that try and not modify a database engine that already exists. And so what they're trying to do is they're trying to insert and query for encrypted data. And the great thing about this approach is that it inherits any new database advance that you get. If you come up with a faster version of a B+ tree, this automatically gets faster. But these schemes tend to leak at initialization time about the entire data set. And it's worth noting that most commercial products use some variant of a legacy scheme. The other approach is what we call custom. And so here, people rip out the unprotected database and build a new database from scratch that is designed to handle protected search queries. These schemes tend to only leak at query time and tend to have lower leakage, but also worse performance than legacy scheme. We also single out a subclass of this that we call oblivious schemes that really work to hide identifiers between repeated queries. And so they leak only structure, but currently they require multiple servers to get something close to efficiency. Okay. And so what we find is that security-wise, these 3 types have very different performance, functionality guarantees, as well as security guarantees. And we find that legacy schemes are most appropriate to use when your data has high entropy and is sparse. Custom systems provide much better security guarantees if you're only going to be getting a small fraction of the database backend queries. And finally, oblivious schemes should be using if you're regularly getting a large fraction of the database back. Okay. So that's what I wanted to say about security, and in the time I have left, I'll talk about functionality. Okay? So I'll talk about utility. Now, utility we view as some convex combination of functionality and performance. Okay? And so the first thing we did is we developed a database instrumentation platform as well as a data and query generator that's been used in a lot of prior work to come up with their performance results. This should be open sourced within the week, but you can bother me and I'll tell you when it gets out. And so this is how we characterize performance of these schemes, and we test them at large scale up to terabytes. The second thing, which is how do we measure functionality, is a little bit more difficult. The natural thing you might want to do is say, well, what fraction of an unprotected database language is supported? But no cryptographer goes out and the first thing they do is implement syntactic sugar. They want to focus on core functionality. And so what we find systems actually do is they focus on one or two base queries using cryptography. And the examples we find in the literature are keyword equality, range search, Boolean combination, and some specialized systems. And then what they do is they combine these base queries in a black box way, in a way that doesn't depend on the cryptographic implementation. So for example, you can turn a range search into an equality search for just searching for everything between A and A. And this approach is important because it allows you to expand functionality quickly, but it also tends to be less efficient and have more leakage. So both of these approaches we find are valid. Okay. So I said that the thing we'd really like to do is ask what fraction of a language is supported, and that seems to be difficult. What's a little bit more manageable is we actually find that unprotected systems have the same approach. They come up with a mathematical basis for queries that they want to answer, and then everything else is answered using a combination of those queries. In particular, SQL has the set theoretic mathematical basis of union, set difference, join, projection, and selection. And so rather than trying to evaluate the entire SQL language, we just look at these 5 things and ask, have we covered these base queries, and do we know how to combine them together in the same way that you can in an SQL system? And we find this is really important well, the first thing we find is that when we look at this approach, we can say, oh yes, we have 4 out of the 5 of these pretty well covered, and there's some more work that needs to be done on join. So this allows us as a community to focus our efforts a little bit more. And the second thing it allows us to do is look forward. So SQL was introduced in 1970, and it became the dominant database paradigm in 1970 with commercial open source systems. And so when cryptographers started working on protected search in the mid-90s, we said, oh yes, we'll go secure SQL. And we went off into crypto land and started doing that. And while we were doing that for the last 20 years, you had NoSQL key value come out, you had graph databases come out, you had NewSQL come out, you had Polystore databases come out, and we're now 4 to 5 database generations behind. And so the question to ask is, how can we possibly catch up? If we start working on key value systems now, well, they're going to be 6 generations behind when we catch up. So the last thing I want to leave with is we think this basis and combination approach is the key to getting protected search up to unprotected database search and getting it actually used in the real world. In particular, we're advocating a 3-pronged approach, which is cryptographers and database experts work together to do 3 things. First, we identify base queries that are going to be used across database paradigms and make these as efficient as possible. For example, keyword equality. Second, we say, does an emerging database paradigm, does it have new base queries? Or does it just focus on different functionality aspects than what we've seen before? And then we quickly fill these gaps using combination approach, so that we're not always trying to redesign crypto from the ground up every time there's a new database paradigm. And with that, I'll stop and take questions. Thanks, everyone.
So we have some time for questions. So I'll start, and I was wondering, the approach that you outline of securing the SQL operations makes a lot of sense. But I wonder, now that we're in the age of data analytics and machine learning and data mining, what role do you see to approaches that will try to provide some sort of security for these types of inferences made on the data?
Yeah, I think this is a hugely important question. So one of the things I didn't talk about, we did the same question of how much of NoSQL have we covered, and there we find the main gap is actually keeping up with insert rates. We actually have the query functionality down pretty well. One of the things the community has done a very poor job in is with graph analytics. And these are often done in sparse matrix computations. And so we need algorithms that not only are doing matrix multiply and addition, but are doing this over sparse matrices that are stored securely. So I think it's a great area to look at, and the community is just starting to realize there's some work in the last couple of years on graph analytics, but it's very fresh and it's a very fertile ground.
All right, well, let's thank the speaker once more, and